Okay, this is lecture 20 of the Quantum Computation and Information course, and this is about lower bounds for the quantum query complexity model, and specifically the lower bound technique known as the adversary method. So let me begin by recapping what the quantum query model is. Oops, have a little highlighter there. So the quantum query model is a model in which many quantum algorithms work. And the way you can think about it is that there's some secret input string, W, which is capital N bits long. It could be from a larger alphabet, but we'll focus on strings of bits. And you can query any coordinate j you want to find out what is the jth bit of the input, W sub j. In fact, you can query superpositions of the coordinates, because it's the quantum model, of course. And precisely what that means is you're given access to some q sub w, plus or minus, which implements the quantum transformation that takes a coordinate ket j into either plus or minus ket j, and that plus or minus is depending on whether the jth coordinate of the input string, w, is 0 or 1. Okay, so it negates the jth ket amplitude if and only if the input string has a 1 in the jth coordinate. Now what you're trying to do is solve some fixed decision problem, let's call it phi, on the unknown string w. And in the quantum query model, the main feature is the cost model, which says that the only thing that we're going to count is the number of queries you make, the number of quantum queries you make, the number of times you use this q sub w plus or minus. Other computation is totally free, so we're not going to count gates or anything. You can think about what you want to query as much as you want. We'll only count how many queries you make. So the classic example, and the one that is related to Grover's algorithm, is when this phi problem is the OR function. In other words, it's a simple task of deciding whether the string w has at least one 1 in it, or whether it's the all zero string. So this is the quantum query problem, or the decision problem that Grover's algorithm can solve with around square root n quantum queries. So at most some constant times root n. That's the Grover search algorithm. And in general, the way you should think about one of these decision problems phi is that there are two sets of strings called the yes strings and the no strings. And you know, the algorithm is supposed to say yes or accept any w which is in yes, and is supposed to say no or reject any string w that's in no. So let's try and tell the difference between the yes strings and the no strings. And in the case of the OR function, the yes strings are just all the n-bit strings that have at least one 1. And the no strings, well, this is not much of a set. It only has one string in it, the all zero string. Okay, and in general, it doesn't have to be the case that all the strings in yes and no can make up all the strings. If that happens, then phi is called a total function. Otherwise, it's called a partial problem or a promise problem. Okay, so that's the quantum query model, and we're going to now show some lower bounds, show some negative results about how efficiently even quantum algorithms can solve some of these query problems. Okay, so how can we prove lower bounds on quantum query algorithms? And by the way, it's nice that we can, unlike the usual, gate complexity or time complexity model where it seems quite hopeless to prove lower bounds. In this limited query complexity model, we really can prove strong lower bounds. Well, it all started with a paper by Bennett, Bernstein, Brassard, and Vazirani around 96 that actually predated Grover's algorithm, and they showed that just for this OR problem that Grover's algorithm solves, a constant times root n queries are necessary. You can't get away with anything less than that. And they called their technique for proving this the hybrid method. Not too long after, a very notable paper by Eels et al. From 98 developed a new method for proving quantum query lower bounds called the Polynomial Method, which we actually won't talk about. Subsequent to that, Andres and Binus in 2000 showed another technique quite different from the Polynomial Method called the Adversary Method. And it was actually kind of, in a way, an extension of the hybrid method. So these are kind of linked. Maybe the hybrid method could be thought of as a proto-adversary method. And I put basic in parentheses there because there were future developments. So after Binus's paper, there are many variants and extensions of the adversary method proposed. And they kind of culminated in a method due to Hoyer, Lee, and Spelek from 2007, which they called the negative weights adversary method, but which now people I think just call the general adversary method. And it seemed to be the sort of strongest variant of the adversary method. It was the method that seemed to be able to prove the highest lower bounds. And an amazing result from 2 years later by Reichardt it was actually shown that the general adversary method is optimal in the sense that it always produces the best lower bound, in the sense that there's always a matching upper bound up to constant factors. In other words, there's a matching query algorithm. So in principle, this general adversary method tells you exactly how many quantum queries you need to solve any decision problem, be it total or promise. Now, there's still things to do. I mean, it's a little bit hard to use in general, but it's kind of amazing that they showed this tight result. But we're not going to get to that. We're going to focus only on the basic adversary method in this lecture. So let me just remind you about the thing we're up against. This is a picture of sort of a generic T-query quantum algorithm. And you see, here are the pieces of it. So on one hand, you're allowed to have unitary gates, as you always are. And since we don't really care about, how many gates you use, we can just stick them all together into one gigantic unitary, because, we're not concerned about that cost. And you also have these quantum query gates or oracles, which actually are how you interact with the input. So notice that they operate on log n qubits, because they sort of take in the name of an index between 1 and n, or between 0 and n minus 1 if you prefer, and tell you information about w's bits in those coordinates. Okay, but the algorithm is also allowed to use additional qubits, and we call this the workspace. And so in general, the algorithm will alternate between doing some computation, which involves all the qubits, and then doing a query, and then doing some more computation, doing a query, and so forth and so on. And it can end with, oops, I advanced the slide there. It can end with one more unitary, and then it can do a measurement at the end, and that'll help it decide whether W is in the set yes or in the set no. Okay, so that's a T-query quantum query algorithm. Okay, and that's what we're going to try to show doesn't exist for various decision problems phi, in particular the OR function. Okay, so now let's say you have some algorithm that supposedly solves this decision problem phi, which has two sets of strings yes or no. And by the way, you can assume that it always starts out with all qubits initialized to zeros. And let me mention also that this is the fixed algorithm, and it differs for differing input strings w through the behavior of q sub w. So no matter what all the input is, these unitaries are the same, but different things happen because q sub w plus or minus implements a different unitary transformation depending on what the input w is. Okay, so in particular, let's define this quantum state, phi sub w superscript 0, to be the state of the qubits after the first unitary transformation. In other words, it's just this u0 applied to the all zeros state. Okay, now the next thing that happens is that a query is performed, and that actually differentiates the state depending on what w is. And then another unitary is performed, some computation, and we get what I'll call psi superscript 1 sub w. Okay, and so forth and so on. And in general, we'll let psi superscript little t sub w be the state of the algorithm when the input is w after the little teeth unitary transformation. Okay, so it goes from psi 0 up to psi capital T if there are t queries. Now, the name that Ambanius chose, the adversary method, is not going to be made extremely clear why he chose it in this lecture. So let me just use the word one time here. Let's imagine that an adversary looks at this algorithm that you've supposedly made that makes t queries for solving the problem psi, and the adversary picks some particular string y, which is a yes string that the algorithm is supposed to say yes on, and also a particular string z, which is a string that the algorithm is supposed to say no on. And the adversary sort of considers running your algorithm with two possibilities, either w being y or w being z. Okay, and that's going to lead to a different succession of psi's as the algorithm goes along, depending on whether w is y or w is z. Well, I say different, but it's only different once you make at least one query. In particular, if you focus on this psi 0 sub w, it will have the same value regardless of whether w is y or w is z, simply because the algorithm's behavior only, until this point, only involves applying a unitary to the all zeros state. So the differing values of w hasn't made a difference yet. Right, so whether the input is y or z, the psi 0 states are the same. Another way we can say that is the inner product between psi 0 y and psi 0 z is 1. This simply says that they're the same state. Okay, so psi 0 y and psi 0 z are the same state. They have inner product 1. But this can change, of course, as the algorithm proceeds. And in particular, let's look at psi superscript t sub w, the final state, in the two cases of w being y or w being z. Well, one thing I want to say is that at the end, it better be the case that the inner product between psi yt and psi zt is not equal to 1. It must have changed. And the reason for that is clear. If the inner product were 1, it would mean that psi sub y and psi sub z were still the same at the end of the algorithm. And then this measurement would have, no way of telling the difference between them. You would get the same measurement statistics, whether you're working with w being y or w being z. But that is impossible if the algorithm is supposedly solving this decision problem, because it's supposed to give the answer yes with high probability when y is the input, and no with high probability when z is the output. We can't do that if, it's always working with the same two states. So in particular, as I said up here, the algorithm has to be able to discriminate between the state of the quantum state at the end of the algorithm when the input is y versus the quantum state at the end of the algorithm when the input is z, because it has to accept y with probability at least 2/3 and reject z with probability at least 2/3. So in fact, more than that, it better be the case not just that the inner product is not 1, but it shouldn't also be like 0.99999 either. It shouldn't be like extremely close to 1. Intuitively, because that would mean the state psi sub y and psi sub z are extremely close at the end of the algorithm, and therefore they have extremely close measurement statistics. In particular, I'd like to claim that their inner product, and indeed the absolute value of the inner product, has to be at most 0.99. Under the assumption that the algorithm works with high probability, it gives the correct answer with probability at least 2/3. And the reason for that basically goes back to lecture 4.5, when we talked about discriminating two qubits, or in general two quantum states. We saw there is if you have any two quantum states, u and v, they don't even have to be qubit states. The extent to which any measurement can tell the difference between them is just a function of the angle between them. And we gave an exact formula there. If you were allowed two-sided error, you could distinguish between two states at angle theta with probability error something like 1/2 minus 1/2 sine theta. The formula is not too important. It's just to say that we know since y is a string where the algorithm is supposed to output yes, and z is a string where the algorithm is supposed to output no, it better be able to distinguish between these two final states, psi sub y and psi sub z, with good probability with error less than 1/3. And in particular, that means the angle between these two states better be pretty, not too close to 0, and also not too close to 180 degrees, because 180 degrees and 0 are the same thing. That's why we're allowed to have these absolute value signs here. I did the calculations. I think they have to be like at least 20 degrees apart if you want to have error 1/3, but it's not so important. Let's just say that at any rate, to be conservative, the inner product, or in fact the absolute value of the inner product between psi y and psi z, had better be bounded away from 1, say at most 0.99. Okay. So what we see now is when you're considering running the algorithm with a yes input y or a no input z, the state of all the qubits, psi y and psi z, starts out with the inner product 1, but at the end it better get into the case where the inner product in absolute value is at most 0.99. So an interesting idea here is to try to define like a progress measure. So we'll imagine, for example, this won't be the final idea, but it'll be the idea for now. We define something called progress sub t, which is just the inner product between the state at time t when the input is y versus the state at time t when the input is z, in absolute value. And under this definition, let's suppose we manage to show that the progress cannot change too much in each essentially step. So a step is a query plus a unitary transformation. Let's say somehow we manage to show this progress can change by at most some delta on every step. Well, we see that it has to get from 1 down to 0.99, and if it can only go by delta, and at most delta in one step, then it's going to take proportional to one over delta steps. Let's say 0.01 over delta steps in order to do that, and that proves a lower bound on the number of queries, capital T, made by the algorithm, something like constant over delta. And that's exactly what we're shooting for. So that's sort of the basic plan of the adversary method. And one nice thing about it, this is quite pleasant, is that you see each sort of step involves a unitary and a query. But unitaries, basically by definition, have the property that they do not affect angles or inner products. If you have two states and you apply the same unitary to both of them, the inner product between them does not change. And therefore, this progress measure that looks at the inner product between psi y and psi z, it's completely unaffected by any of these unitary transformations. And that's really cool. It means we can just forget about them. And in order to attempt to prove this statement about the progress only decreasing very slowly, it suffices to show that the query steps cannot change the progress very much. And that's the thing that, of course, distinguishes, w equals y from w equals z, the queries that are made. Of course, what we'll want to see in the future is that it's easier to show that not a lot of progress is made if y is similar to z. Maybe they don't differ on very many coordinates. That intuitively is the case when making your query with q doesn't change much. Okay. So, as I said, this is a good idea, but it's not the final idea. This idea is a little bit too simple. And let me explain why. You see, it's not enough to focus on a single string y in the yes set and a single string z in the no set. And the reason for that is, well, suppose, you could show all this and show the lower bound when you just focused on a single y and a single z. Well, what would that effectively show is that any algorithm that just gets this single y string correct and this single z string correct must require a lot of queries. But that doesn't make sense, because if the algorithm knows it only has to tell the difference between this particular y and this particular z, well, they're distinct strings, so there must at least exist one coordinate j where they differ, and then the algorithm can tell the difference between that specific y and that specific z with one query. It just has to make one classical query on the jth position, and it'll know if the input is y or z. Okay, so that only, it can always do this with one query, so we have no hope of showing like a really large query lower bound like this. So all this is saying is that we can't focus just on a single y and a single z. We have to focus on a bunch of y's versus a bunch of z's. Okay, so we're going to have to make a more sophisticated progress measure, but this is the general idea. Okay, well, I can now tell you the final statement that we're going to spend a lot of time trying to prove. And this is not even the full statement of the basic adversary method as proven by Mbinus. It's like an even simpler version of it that I'll call the super basic adversary method. But it illustrates most of the ideas and gets us most of the good conclusions. So let's take a look at it. So we're assuming we're interested in some decision problem phi with a set of strings, a yes set of strings and a no set of strings. And we're going to pick out a subset y of the yes strings and a subset z of the no strings. Not necessarily all of them. It's up to our how we're planning to use this method. And what we want is these two subsets y and z to have some nice property. So we want two things. The first one says for every string little y in the set capital Y, there's a lot of strings, m strings, in the set capital Z, which are very similar to y. Okay, so this distance between y and z is the Hamming distance. This is the number of coordinates on which y and z differ. Okay, so they're particularly similar if the Hamming distance is 1. They only differ on one coordinate. And this bullet point here is saying we want it to be the case that for every string y in capital Y, there's lots of strings in capital Z that look very similar to y. They only differ on one coordinate. And conversely, we want the same thing in the other direction, that for every string little z in our set big Z, there's a lot of strings, some m prime strings in y, capital Y, that are very similar to z, so that, again, the Hamming distance is 1. So there are many pairs of strings, essentially, in capital Y and capital Z that look very similar. They only differ on one coordinate, even though the algorithm is supposed to say yes on the y strings and no on the z strings. Well, the theorem tells you that if you combine these two sets y and z with these properties, then you get a lower bound for the quantum query complexity of psi. You show that any algorithm that solves psi needs this many queries proportional to the square root of m times m prime. So you really want m and m prime to be large for this. And I think specifically we'll show that it's at least 0.005 times m prime square root, but don't get too concerned about the constants. We just want to show that it's at least proportional to the square root of m prime. Okay, so it'll take a little effort to prove this theorem. So before we get into that, let's actually talk about how to use this theorem to derive some consequences. Okay, so let's start with the main thing that I've promised you for a couple of lectures now, a lower bound for any quantum query algorithm deciding the OR problem. This is the decision Grover problem. In other words, given a string W, does it have at least one 1, or is it the all zero string? And actually, with this problem, you'll see why we want this sort of potentially asymmetric relationship between m and m prime. So what sets y and z are you going to take? Well, I just wrote it in the case of n equals 6 here to make it more vivid. Let's actually look at the z set first. I mean, z has to be a subset of the no strings, and there is only one no string, the all zero string. So, I mean, you pretty much have to take z to be the single string of all zeros. Now, what about the y set? Well, you're basically forced here too. Y has to consist only of strings that are yes strings, so they have to have at least one 1. And in order to get these two properties where there are, a number of pairs of yz strings at Hamming distance 1, it better be the case actually that all the strings in y have exactly one 1 in them. Okay, so all of which is to say that you should take y to be the set of all strings with exactly one 1. Okay, so now we just have to ask ourselves what values of little m and little m prime can we take? And then we pop out our lower bound. Well, let's start with little m. So little m is about, for each string in y, let's say this string, we need to show that there are at least m strings in z that are within Hamming distance 1. Well, there is only one string in z. Luckily, it is at Hamming distance 1, so you see that we can take m to be 1. Now, what about m prime? Well, for m prime, we have to look at all strings in z. Well, there's only one of them, the all zero string. And we have to ask how many strings are there in capital Y that are at Hamming distance 1. And luckily, all of them are at Hamming distance 1, and there's capital N of them in general. Okay, so we can take m to be 1, m prime to be capital N, and therefore our quantum query lower bound that we get is the square root of the product of those two things, which is square root n, which is exactly what we want. This is the lower bound that matches Grover's algorithm, Grover's upper bound of proportional to square root n. So you see that even with the super basic adversary method, we prove the desired quantum query lower bound for the OR problem. Okay, let me throw in a couple more examples since we have this nice theorem ready. Here's a generalization of Grover's problem. For a parameter k, let's say you're trying to decide whether W has at least k1s or less than k1s. So the problem we just saw is when k is 1. That was Grover's algorithm, but you can think about it for general k. A nice example is when k is n over 2. So then you're trying to decide if the unknown string W has more or less than half of its coordinates being 1. And this problem actually gets harder the larger k is. And there's a natural choice for what capital Y and capital Z should be for this problem. For capital Y, you'll just take all the strings that have exactly k1s, and for capital Z, you'll take all the strings that have exactly k minus 1 ones. So indeed, these are sets of yes strings and no strings, respectively. And now we just have to compute m and m prime. So for m, you have to look at each string in y and ask how many Hamming distance 1 strings are there to that string in y, that is in z. Well, for each string that's in y, it has exactly k1s. And if you turn any of those k1s to a 0, that puts you into z. So we can take m to be k. And there's a similar story for m prime. If you have a string that's in capital Z, so it has exactly k minus 1 ones. In particular, that means it has n minus k plus 1 zeros. And now if you turn any of those zeros into a 1, you get a string that's in y, a string with k1s. So m prime can be n minus k plus 1. And therefore, the quantum query lower bound you get is the square root of k times n minus k plus 1. This is a little tricky looking. You see, if you take k to be 1, that gives you square root n. you can assume basically without loss of generality or imagine that k is bounded by n over 2, in which case n minus k is sort of just proportional to n. So basically in this case, you get a lower bound that's like square root of k times square root of n. So you see it grows harder as k gets larger. And in particular, what's interesting is if k is, let's say, n over 2, that's a nice case, the problem of deciding whether w has more or fewer than half ones, the lower bound is proportional to capital N. So this actually shows that that's a really hard task, even for quantum query algorithms. You need to query proportional to n coordinates. Basically, it's the same as just, querying everything up to a constant factor, which is the trivial solution. So it actually shows an example of a hard problem where quantum doesn't really give you any advantage. I'll run through one more example. It's not so closely related to things we've seen before, but it's it's for historical interest. Here's a final example. Quantum query algorithms are actually quite good at evaluating formulas over the input word w. So here's a simple Boolean formula. It's an root n way and of root n way ors of the w bits. So you break up the w bits into square root n many blocks. You do an or on each block and an and on the blocks, and that's supposed to be the output of phi. Okay, so that's a little bit funny. In other words, the yes strings are all the strings w that have a 1 in each block, at least one 1 in each block, and the no strings are all the strings that have a block of all zeros. Okay, so you're trying to use queries to tell the difference between a yes string and a no string. And it's not hard to show that this requires linearly many queries in the classical case. Okay, so how are we going to use a super basic adversary method on this? Well, you let y be all the strings that are kind of minimal. They have exactly 1, 1 in each block. You let z be all the strings that are sort of maximal. They have, they're all zeros block, but they only have one all zeros block. And every other block has exactly 1, 1 in it. Okay, and again, you compute your m and your m prime. So your m, you look at all the strings in y. There's exactly 1 per block. For each block, you can turn off a 1 to a 0 and get a string in z. So that means m is root n because they're root n blocks. And conversely, if you take any string in z, it's got an all zeros block, which is kind of unsatisfied, but all the other blocks have exactly 1, 1, so they are satisfied. So you can flip each coordinate from a 0 to 1 in the all zeros block, and you'll get into y. So again, that means you can take m prime to be root n. So the square root of m prime is just, again, square root n. So this shows a lower bound of square root n for this problem. You might ask if that's good or not. It's good. It was known previously that with some careful use of Grover's search, you can actually solve this quantum query problem with proportional to root n queries. Okay, and so Ambinus used his adversary method to show that that is sharp. And in particular, this is a lower bound that can't seemingly easily be attained by the polynomial method, this other method that people use to prove quantum query lower bounds. So it's an example showing the strength of the adversary method. Okay, so that's going to be it for examples. So now we'll come to the proof. How do you prove this theorem, the super basic adversary method? Well, we've kind of alluded to the plan already involving a progress measure that decays slowly, but we'll have to get into a more sophisticated description of that now. Okay, so we're assuming now that phi is some problem, and we've got our y and our z set up that satisfy these two properties. Now, what we're going to do is define a set of pairs R. You can think of R as standing for relation, if you like. It's all the pairs y, z, where y is a yes string from y, little z is a no string from capital Z, and the Hamming distance between them is 1. Okay, so these pairs are sort of like particularly challenging pairs of inputs for the algorithm, in the sense that the algorithm needs to give different answers. It needs to say yes to y and no to z. But that's tough because there's only a single coordinate on which they differ. Okay, so you can think of this R as like the really challenging pairs. And our two assumptions about the sets capital Y and capital Z give us some information that we'll use later about the size of R involving m and m prime. Okay, so this set R of pairs is going to be quite important throughout the proof. Okay, so now we're going to define the progress measure, which looks a little bit more complicated than before. Again, we'll let psi superscript t subscript w be the state of the algorithm when the input is w after the tth query. And we'll define the progress amount at time t, not just to be this is what it was in our sort of illustrative example, but we'll actually sum over all of these difficult pairs y, z, and r. So the progress measure at time t is the sum over all these pairs y, z, and r of the absolute value of the inner product between psi y and psi z at time t. So it's sort of an aggregate measure of how well the algorithm is doing at time t, and sort of telling the difference between yes strings and no strings. You know, telling the difference between these difficult pairs in capital R. So it's somewhat natural. And let's see, what can we say about this progress measure? So first of all, the progress measure at time 0 is capital R. That's of course it's after the 0th query, when we haven't done any queries. Psi y and psi z are the same. You know, nothing's happened to distinguish the state of the algorithm because we haven't done any queries yet. Okay, and that means all these absolute values of inner products are 1, and there's cardinality of R of them. So the progress measure at the beginning is cardinality of R. On the other hand, we claim at the end, at time capital T, after all the queries have been done, the progress measure had better be smaller than 0.99 times capital R. That's basically for the reason we saw before. We know that for all pairs yz in the relation capital R, you know, y is in y, you're supposed to say yes to it, and z is in z, you're supposed to say no to it. So it better be the case that at the end of the algorithm, that little t should be a capital T actually, at the end of the algorithm, the inner product between psi y and psi z in absolute value should be at most 0.99. And that should hold for every pair yz in R, and therefore at the end of the algorithm, it better be the case that the progress measure is bounded above by 0.99 times cardinality of R. Okay, so we're in the setup we want. The progress starts out high and has to end a lot lower. And what we need to show is that it can only go down by so much as you make queries. Okay, and indeed this is going to be the key claim right here that we'll spend all our time proving. It says that for any t, any stage of the algorithm, the difference in progress between progress at time t and times t plus 1, in other words, the difference in progress that you can attribute to the tth query, is bounded by this quantity, which is cardinality of R times a small factor, 2 over square root mm prime. And that's actually going to prove the theorem, which is great because you see progress starts at cardinality of R, it goes down to 99% of that, and as it's going down, at each step, it can only go down by a fraction of R, which is like 2 over root mm prime. So basically you need reciprocal of this many steps, root mm prime over 2 steps. Well, again, times 0.01 because you only have to go 0.01. Don't get too hung up about the constants. It basically shows that capital T, the number of queries the algorithm makes, has to be at least proportional to this reciprocal of this tiny amount. In other words, proportional to root mm prime, which was our goal. Great. So this claim, if we can show it, will complete the proof of the theorem about the super basic adversary method. So let's collate all the pieces up here on top and turn our minds to proving the claim. Now, before we get to proving the claim, let's tarry a moment. We won't dive into analyzing the tth query. We'll actually just mess around a little bit arithmetic-wise with this bound we're trying to prove. So let's take the statement that I just brought down from the top here, that for each string y in capital Y, there are many strings, m strings in capital Z, that are close in having distance to y. Well, one thing that this means is that for every string y in y, it has at least m mates z that are in capital R. So that simply shows that capital R has to be at least m times the cardinality of y. Similarly, I mean, because each string little z in capital Z has m prime mates in capital Y that are in R, it shows that cardinality of R has to be at least m prime times cardinality of Z. Okay, that's very simple. This is how we use our hypotheses. So let's just add these inequalities together and get that 2 times R is at least m cardinality of Y plus m prime cardinality of Z. Okay, well, that's great. And that's all we'll use about the hypotheses. But now let's take a look at something interesting here. we have this 2 times r, 2 times cardinality of r in our claim. And we just show that 2 times cardinality of r is bigger than something. So in fact, the claim would be an even stronger claim, and therefore it would, even better finish the theorem, if we could prove it with the right-hand side being this smaller quantity. Well, we need to keep this 1 over root mm prime times m cardinality of y plus m prime cardinality of z. Okay, so this quantity we've just shown is less than or equal to our target upper bound. So if we could show that as an upper bound, it would be even better. Okay, so in fact, that's what we're going to do. Okay, and let's do a little arithmetic. We'll distribute it and get these funny looking factors. So it's starting to look a little complicated, but, well, hang in there. Okay, so that's the stronger upper bound we're going to prove. So let's plug in it up there. And now we've actually used the hypotheses, so we don't need to show them anymore. And this is what we're going to get down to. We want to show that for every t, the progress difference here is bounded by this funny factor times the cardinality of y plus this funny factor times the cardinality of z. Okay, these two factors are reciprocals of each other. Okay. Now, again, before we get into the queries, let's make some more observations. One is that, as I said before, the unitaries in the quantum query algorithm don't affect the progress at all because they don't change inner products. We can basically forget about their entire existence and just think of the algorithm as a sequence of calls to the query implementer, q sub w plus or minus. Okay, so we want to prove this claim for all t, so let's henceforth, just for the rest of the proof, fix any particular t and any particular t plus 1. We'll kind of call that before the tth query, or I guess it's supposed before the t plus first query, and after the t plus first query. And we'll also, for quite a long time, fixate on one particular pair, yz, in this relationship R. So where, again, y is a string in capital Y, z is a string in capital Z, and they have Hamming distance 1. And we're going to really imagine, like, what's the difference between what the call to q does on little y at time t, or t plus 1, and what it does to when the input is z at time t plus 1. So for this pair y and z, of course, they differ on exactly one coordinate. That's part of the definition of capital R. And let's call that coordinate j star. Okay. So, let's focus actually even further just on y. Okay, so let's imagine running the algorithm when the input is y and focus on the state of the algorithm psi sub y superscript t before the t plus first query. And then imagine what it is after we do that t plus first query. So again, let me draw the picture of the quantum query algorithm. It looks sort of like this. And again, as I said, we can totally forget about the unitaries. They're irrelevant to us. And let's say this is the t plus first query, this call to q. And again, we're assuming the input is y here. Okay, so this is the state of the algorithm just before the query. This is the state of the algorithm just after the query. And now we want to understand, how things change when we make that query. Okay. So actually, let's look again at this. You see, the query, the quantum circuit algorithm has two different kinds of qubits it's working on. It has this input register and the workspace register. Okay, so every quantum state you can think of having like a piece corresponding to the inputs or the coordinates, and also some sort of work coordinates. And the input coordinates, store quantities that are log n qubits long, and so we think of them as an index into capital W. That's either ket 1, ket 2, etc. up to ket n. So if we sort of collect like terms, whatever psi is at time t, just collect together all the piece of that quantum state that has ket 1, all the piece that has ket 2, all the piece that has, etc., ket n. And so the state in general can look like ket 1 tensor some stuff, ket 2 tensor some stuff, ket n tensor some stuff. Okay, now what we'd like to understand is sort of how much amplitude psi y has on each of these pieces. So we should rewrite it a little bit so that it becomes more clear. So let's let, whatever this jth stuff is, let's let phi sub j be a unit vector in that direction. So we'll normalize each of these stuffs so that it's like coefficient times psi j. See, so let me rewrite it like this. So this is a sort of a better way to write it. It's amplitude alpha 1 times ket 1 times a unit vector, tensor unit vector I should say, plus amplitude alpha 2 times ket 2 tensor unit vector, and so forth. Okay, so alpha 1 through alpha n kind of measure for this quantum state right before we do the t plus first query, sort of how much amplitude the query there's going to involve for each of the capital N coordinates 1 through capital N. So just a reminder here, these phi's are unit vectors, and of course the sum of the squares of the amplitudes has to be 1 because it's a quantum state. Okay, so now we do a quantum query, and that's actually the method by which we go from psi t to psi t plus 1. Again, still focusing on the input being y. So what does this quantum query do? Well, if you recall, it changes the amplitudes of each piece depending on the the input bits. So in particular, for the piece on ket j, for example, j being 2, it potentially negates this amplitude depending on whether y has a 0 or 1 in the jth coordinate. Okay, so the after state, psi sub y superscript t plus 1, looks kind of similar, except all the amplitudes have potentially a minus sign on them, again, according to the coordinates in the input y. Okay, so that was for y. Now let's focus on z. Now the state of the algorithm at time t, when the input is this particular z, could be totally different, but let's put it into the same form. Okay, so let's write it as beta 1 times ket 1 times some unit vector psi 1 plus beta 2 times ket 2 times some unit vector chi 2, etc. Okay, so again, the chi's are unit vectors, and the betas are amplitude whose squared moduli sum up to 1. Okay, so it could be a quite different state. Well, how different it is from psi sub y, goes into our progress measure. And of course, it changes once we do the t plus first query in the same way that psi y changed. These beta amplitudes potentially get negated depending on the coordinates in the string z. So they have these signs that are like -1 to the zj. Okay, and one thing that we're going to use in a second is that the strings little y and little z are very similar. They only differ on one coordinate, namely j prime. And so actually, all these sign changes are pretty much the same, except in the j star coordinate. Okay, but before we get to that, let's look at some inner products, because these are the things that go into the progress measure. Okay, so before we do the query, the progress measure asks us to look at the inner product between psi y and psi z. So I have to compute the inner product of this and this. Now, if you take the inner product, you turn this into a bra and multiply them. It looks like you'll get a lot of cross terms, but actually you only get capital N terms because, ket 2 is orthogonal to ket 1, and, any two index kets, I and j, are orthogonal to each other unless I equals j. So actually, it's not so bad. The inner product between psi y and psi z looks like this. It's the sum over all coordinates j of, well, the complex conjugate of alpha j times beta j times the inner product between phi j and chi j. Okay, so, you'll get some linear combination of things that look like this alpha bar beta times the inner product between these phi and chi vectors. Okay, that could be whatever it is, some complicated quantity, but what we're going to claim is that the thing you get in the after case is not very different. So let's look at the after case, and as I mentioned, all of these signs are the same, except in the case of j star, where they're different. Okay, so in particular, again, the inner product will look similar, and all these same signs will cancel out, except in the j star case. Okay, so what that means is the inner product here looks extremely similar to the inner product here. In fact, it's completely the same except for the j starth term, the term corresponding to the coordinate where little y and little j are different. And there you'll get a minus sign. Okay, and now you start to see, this is one of the, these two inner products are two things that contribute to the progress, and you'll see that, yes, they don't change very much, and that's why we can hope that the overall progress doesn't change very much. Okay, so a natural thing we're going to do will be to subtract these two quantities. I hope you think that's natural. So when we subtract these two quantities, the difference between them is mostly 0. We only pick up 2 times this piece. So we get 2 times complex conjugate of alpha j bar times beta j bar times the inner product between phi j bar and chi j bar. And we want to sort of upper bound this, so we're going to take the magnitude of both sides. And so this is the magnitude of the difference. And for this, mystery phi and chi, we can't really say much about them except that they're unit vectors. So the inner product, the magnitude of their inner product is at most 1. So we'll just delete that. And then we get the magnitude of the rest, which is 2 times magnitude of alpha j star times magnitude of beta j star. Okay, so finally, that's sort of the upper bound that we get on the difference between these two inner products. It's, 2 times the product of the magnitudes of these two amplitudes, the j star amplitudes. Okay, well, there's a lot of math going on, but we have to soldier on. So actually one small thing we'll do to make it look even more like the difference of progress is we'll actually use the triangle inequality here. It's a little bit hard to see, and it's maybe also not the way you're most used to seeing the triangle inequality. But here we have the difference of two absolute values, and that's actually at most the absolute value of the difference. That's the triangle inequality, just written in a sort of funny form, or a backwards form. So we'll save that. Okay, so we'll get that the difference between the magnitudes of these two absolute values, sort of the before inner product and the after inner product absolute values, is at most this, 2 absolute value of alpha j star times absolute value of beta j star. And we did that because that's directly going to go into the difference of the two progresses, if you look at the definition. Okay, so let's save this. And it feels now that we should, sum this over all pairs y, j, and r, and start to try to prove something about the difference in the progresses. But again, we're going to wait for a moment and do one more math trick before we get down to business. So this little math trick is a really elementary little math trick that we need. It's basically to take care of the fact that so far we've been treating y and z symmetrically, but because we have this like m and m prime thing where m and m prime could be different, we have to do like a little math trick here to inject some anti-symmetry into the situation, or non-symmetry. So here's a tiny little lemma about real numbers a, b, and a positive real h. It's this. 2 times a times b is at most ha squared plus 1 over h b squared. Okay, there's some kids here in my house that are playing in the other room. I'm gonna try to close the door to keep the volume down, otherwise you can enjoy their shouts. I'm assuming they'll bust into this room while recording. I'm recording in any moment now, and it'll be hilarious. Okay, where were we? We're trying to prove this lemma. There's 2 simple ways to prove it. It's very elementary. Proof number 1, if you know the AM-GM inequality, just imagine dividing by 2 on both sides. So the left-hand side would just be AB. On the right-hand side, you have the average of 2 quantities, HA squared, the arithmetic average of HA squared, and 1 over H B squared. And now the geometric mean of these 2 quantities is, you see the H's cancel out, and you get AB. So that's one proof. If you don't know the AM-GM inequality, here's another proof. Just magically decide to write down this quantity, the square of this real number, root HA minus 1 over root HB. That's the square of a real number, so it's non-negative. And now if we just expand it out, FOIL it out, we get HA squared plus 1 over HB squared minus, and now you see you get 2 times the product of these 2 quantities. The root h's cancel and you get minus 2ab. And this inequality can be rearranged to get this inequality. Okay, great. So obviously we're going to take this little inequality we've proven and apply it to the right-hand side we've got. And our h is going to be this magic quantity root m over root m prime that shows up in the claim we're trying to prove. Okay, so if we do that, then we exactly get this. And now you see it looks even more like the right-hand side of our progress measure. And so we're almost in business. We're really ready to try to prove our claim now. Okay, so let's clean it up once more. We have a few more tidying ups to do, and then there'll be a couple of lines to complete the proof of the claim. So this is what we've proven about the fixed string, the fixed pair YZ in the set R. And it involves this coordinate J star, but we've got a bit of notational sloppiness here because this coordinate J star actually depends on the pair YZ. It's the coordinate in which Y and Z differ. So it would be better to show that dependence and write it as J star of Y comma Z. So let's do that, and we'll now make this look even uglier by putting J star of Y and Z here. And I'll rewrite our assumptions up here. And in fact, even this is not fully notationally correct enough, because to be really scrupulous, so these alphas are the amplitudes that are associated to the state of psi y at time t. So really the alphas depend on y. And similarly the betas actually, they came from the state psi sub z. So they really depend on z. So we should really show that notational dependence as well. So really, to be fully scrupulous, this alpha should have show the dependence on y, and this beta should show the dependence on z, because this whole inequality here is about one fixed particular pair yz in the set R. Okay, so finally what we've shown about particular pair yz in the set R is this difference, which contributes to the progress. And as the screen has shown, what we're going to do is sum this over all pairs yz and R. And finally, that's great, because when you sum this over all yz and R, this first piece, that's exactly progress at time t. And when you sum this piece over all pairs yz, by definition, that's progress at time t plus 1. So finally, summing over all pairs yz and R, we get the difference in progress on the left, and we get some complicated looking thing on the right, which, well, hopefully it at least looks like our target. Okay, let me clean this up a little bit here. Okay, so final thing we have to do is compare this right-hand side, which we've got as our bound, to the target. And even though there's so many symbols in there, we're actually really close. There's only a few lines left in this proof. So let's just look at this first term here. We can take out the root m prime that matches what we need to get, and what we're left is the sum over all yz and R of the square of this complicated looking amplitude. And what would be great is if we could show this is at most cardinality of y, because that would match up with this first term. And of course we can do that, it's the exact same thing for the second term, it will match up with the second term. So really this final claim is the last thing we need to show to complete the proof of the overall claim. And believe it or not, this is actually easy. So to see it, take a look at the sum. It's summing over all pairs yz in the set R, but think of it as first summing over all little y in capital Y, and then going over all mates z, which go together with y in the relation R. So for each fixed little y, if you look at all these z's in R, each of these z's is some string that differs from y on a single coordinate. And, since these are different z's, you have different coordinates, j star yz, where they differ. So you see, for a fixed y, you have some set of amplitudes, this alpha superscript y, and you're summing their squared magnitudes over some subset of coordinates. And you don't sum any coordinate twice, because again, for each y, if you look at all the z's that it matches up with in R, they differ on, different coordinates. So again, for each y, you're summing a subset of all possible squared magnitudes of alpha superscript y, and that's just at most the sum of all of these squared magnitudes, which of course is at most 1. If you remember, these are the amplitudes of a quantum state. So for each little y and capital Y, the sort of inner sum, if you will, over all z's that match up with y is 1. So indeed, this overall sum is at most cardinality of y. And in fact, that completes the proof of the claim, and therefore the overall proof of the super basic adversary theorem, which in turn gave us our lower bound for the quantum query complexity of the OR function and various other functions, the optimality of Grover search. Yeah, you might even forget at this point, like, what was the theorem we were proving, so I just put it back up here. This is the theorem we just proved, the quantum query lower bound that we get from the super basic adversary method. So, that's mostly it for the lecture. Let me just tell you a few more things. So, as I mentioned, I call this the super basic adversary method. The thing that Ambinus proved in 2000 was what he just called he called it the adversary method. Maybe now we retroactively call it the basic adversary method. So what is the basic adversary method? I'll tell you, it looks like this, but it's a little bit more complicated. Yeah, the theorem statement sort of takes up the whole page. It's not that complicated, so let me read it for you here. So this is the basic adversary method, which you can use to prove more interesting things, lower bounds. So again, we have some decision problem phi with some yes strings and some no strings. And again, we're going to pick out carefully some subset capital Y of the yes strings and some subset capital Z of the no strings. And now we're going to let capital R be some subset of pairs, that should say Y and Z, not Y and N, some set of pairs from Y and Z, which will be quote-unquote hard to distinguish. So before, R was just all the pairs that differed in exactly one coordinate, that had Hamming distance 1. But that's not how it's going to be necessarily in the basic adversary method. There's just going to be some subset of pairs. And there's actually going to be several requirements on them. So first pair of requirements is going to be similar to before. We're going to require that for each little y in capital Y, there are at least m matches or mates, z and little z, such that the pair yz is in our sort of hard set, capital R. And conversely, for each little z in capital Z, there are at least m prime strings where the pair yz is in capital R. So that's all looking sort of similar to the super basic adversary method. But there's going to be, a twist. So for each coordinate j, let's define R sub j to be a subset of the hard pairs capital R. It'll be all the pairs that differ on exactly the jth coordinate. Another way you can think about it is like all the pairs which you can distinguish by querying the jth coordinate. Okay, so you look over all your hard pairs capital R, there'll be some pairs that you can distinguish by querying the first coordinate, some pairs you can distinguish by querying the second coordinate. And what we actually kind of want is that none of these sets is too large, because that kind of tells you that there's some coordinate where you can make a lot of progress if you query that coordinate. You can quickly distinguish a lot of pairs of strings in capital R. So we actually want somehow these RJ sets to be small, and that's what the second set of assumptions says. So I'll read it here. It says that for every string little y and capital Y and every coordinate j, there's at most L strings z, which match up with y in the set R sub j, so that there's at most L strings z, such that y and z are a hard pair in capital R, but they can be distinguished by the jth coordinate. And the second assumption is similar. It says for every string little z and capital Z and every coordinate j, there's at most L prime strings y, that match up with z, but have the property that y and z can be distinguished by querying the jth coordinate. So if you finally have these two things, and you want m and m prime to be large, and you want L and L prime to be small, then the basic adversary method gives you a lower bound that looks like square root mm prime divided by square root LL prime. And so this is actually a generalization of the super basic adversary method. If you take R to be all the strings that differ in exactly one coordinate, then you can take little l and little l prime to be 1. You get the same lower bound as before. But this gives you a more general set of tools for proving a quantum query complexity lower bound. So as I foreshadowed there by flicking ahead, we may look at the proof. Well, in fact, I'm not going to look at the proof. I'm going to call it an exercise. And it really is. If you actually look at the proof we did of the super basic adversary method and think about the modifications you would need to prove this more general form of the adversary method that I showed, it's really quite straightforward. I mean, it's really just each of these j stars can get summed at most L or L prime times. It's, I leave it to you as an exercise to work it out. And let me also leave it to you as an exercise to work out the following, interesting use of the adversary method, the more general adversary method. So one thing that we saw about Grover search is that, although it only needs root n queries to find a 1, if it's promised that it's either the all 0 string or there's a single one, it actually has an easier time if there are lots of 1s to potentially find. So we saw that if you're promised that you have a string with k 1s, you can actually find it with a quantum query algorithm that only makes proportional to root n over k queries. Okay, let's assuming k is at most n over 2, and that's better. And in fact, the basic adversary method from the just a few minutes ago shows that this is tight, that you need at least square root n over k queries to solve the associated decision problem of deciding whether a string w has no ones or it has at least k ones. Okay, and you can see for this phi, the no set, which is all the strings with no ones, and the yes set, all the strings with k ones, there are actually no pairs like in the yes set and the no set at Hamming distance 1. So that means you cannot use the super basic adversary method, which is one reason you need the basic adversary method due to m-binus. Okay, and finally, this was the basic adversary method. As I mentioned at the beginning of this lecture, there's more generalizations of it, taking you all the way up to the negative weights method or the general adversary method. But we won't talk about that in the lecture. That's a story for another time.